Hello and welcome to lecture 18 of our course on stochastic modeling of biological processes. In this lecture, we will start our discussion of chapter 7, covering stochastic simulation algorithms for reaction-diffusion advection processes. In chapter 6, we discuss stochastic reaction-diffusion algorithms, which are suitable for modeling systems of interacting particles which are only transported by diffusion from place to place. However, in some applications, active transport also plays an important role. I have listed here a few examples, going all the way from small atomistic molecular world to collective animal behavior. In Chapter 7, an example of the smallest spatial scale is discussed in section 7.5, where charged particles, like ions, attract or repel each other through electrical forces. Considering intracellular processes, molecular motors transport large molecules and intracellular components to their destinations. In the next lecture, we will discuss behavior of bacteria, whose trajectories are biased random walks. So it is not a pure diffusion, they follow chemical cues to find nutrients or avoid toxins. In section 7.4, we will also discuss collective animal behavior, where animals can run, swim, or fly, all in response to external cues to find food or avoid predators. In this lecture, I will show how active transport can be incorporated into the stochastic reaction diffusion algorithms, including both individual-based and compartment-based models. We will start with adding advection to diffusion models in section 7.1, and then we will add reactions as well. Our first model of diffusion, considered in chapter 4, has been a position jump process, where we calculate the position of the diffusing molecule xyz using three discretized stochastic differential equations, one for each coordinate. At each time step, we use three normally distributed random numbers with zero mean and unit variance, and we calculate the position at time t plus delta t from the position at time t by adding a random displacement. Equations 315 to 317 are discretized versions of stochastic differential equations with the zero drift term. One possible way to add active transport into our modeling is to replace equations 315 to 317 by stochastic differential equations with non-zero drift terms, given in the lecture notes as equations 71 to 73. In some applications, the drift vector is a conservative vector field, given as the gradient of a scalar function, which we will call a signal. Assuming that the signal is attracting modeled particles, then they will be aggregating around the maximum of the signal profile. The classic macroscopic description of such a process is given in terms of the chemotaxis equation, which in the case of a simple diffusion advection process does exactly describe the average behavior of the stochastic system. We will highlight this using one-dimensional examples, which model the behavior of the x coordinate. The x coordinate of the drift vector is denoted f with tilde to highlight that it is different from the vector f. We assume that it only depends on the x coordinate, denoting by pxt the corresponding probability distribution function. We know that it satisfies the Fokker-Planck equation in this form, as we have previously shown in chapter 3. If f tilde is the derivative of the signal profile, then the Fokker-Planck equation is written as the chemotaxis equation. In particular, considering individual-based modeling of diffusion advection processes, there is nothing new in section 7.1. We have already presented the underlying theory in chapter 3, where we have introduced and analyzed stochastic differential equations. What about compartment-based modeling? Compartment-based model of diffusion was introduced in section 4.2, where we denoted by AI the number of molecules in the ith compartment and modeled diffusion as this chain of chemical reactions. In applications, the modeled particles does not have to be molecules, but also larger objects, like whole cells, when modeling behavior of unicellular organisms, like bacteria in section 7.3, or in some applications, we call them agents when the diffusion advection model is formulated as an agent-based model. To introduce advection into this diffusion model, we make the jump rates dependent on the drift term. If the drift term is 0, then we recover the original diffusion model, where the jump rate, lowercase d, is the diffusion constant d divided by the compartment size h to power 2. If f is positive, then simulated particles jump more frequently to the right than to the left, and vice versa. The justification of this choice of the jump rates is left to you as exercise 7.2. It is a good practice of the derivation of equations for averages of this chain of chemical reactions. Passing to the limit h goes to 0, equations for the mean vector, mt, converge to the chemotaxis equation. We are illustrating this result in figure 7.1 on page 196. Here we choose the signal profile as a piecewise linear function with its maximum at the point 0.5 mm. Then the derivative of the signal is equal to the positive constant value for x less than 0.5 mm and to the negative constant value for x greater than 0.5 mm. We start with the uniform distribution of 1000 molecules, so we have 25 molecules in each compartment at time 0. A snapshot from this video is in the lecture notes as figure 7.1b. We observe that there is a high concentration of particles around the maximum of the signal. The red line is obtained as the solution of the chemotaxis equation. If we wait for a sufficiently long time, then this distribution will approximate the corresponding stationary distribution, which we can also obtain by putting the time derivative equal to 0. So any local maximum of the signal corresponds to the local maximum of the stationary distribution. Next, we will discuss how we can add advection to reaction diffusion models. In sections 6.1 and 6.2, we have explained stochastic reaction diffusion modeling using a simple reaction diffusion system. Molecules diffuse and are degraded in the whole domain. They are produced in the red part of the domain, and there are initially no molecules in the system. The corresponding compartment-based model is introduced in section 6.1. We denote by AI the number of molecules in the ith compartment, and we describe diffusion as this chain of chemical reactions. The degradation happens in all compartments and the production only happens in the red compartments. To add advection to this model, we need to modify the jump rates d. In section 7.2, we model diffusion, advection and degradation in the whole domain. We modify the jump rates to model the underlying diffusion advection process. Reactions are introduced in the same way as before. Since the resulting model is written as a chemical system, we can use the Gillespie algorithm to simulate it. An illustrative simulation is presented in figure 7.2a on page 198, which is a snapshot from this video. We observe that the molecules are initially produced in the left part of the domain. They diffuse and are degraded, but they also aggregate around the maximum of the signal. We use the same signal profile which we have used in our first example. Signal Sx is a piecewise linear function with its maximum at the point 0.5 mm, which is also the maximum of the long-time behavior of the concentration profile. The black line is obtained as the solution of the deterministic partial differential equation model, which also provides a description of the average behavior of the stochastic model. The black terms of this partial differential equation has already appeared in chapter 6. The red term is the new one describing the drift term. The molecular-based model of this reaction diffusion system is presented in section 6.2 as the stochastic simulation algorithm A17 to C17 on page 165. It uses the stochastic simulation algorithm A8 to C8 from section 4.1 to describe the trajectory of each molecule, which is based on this discretized stochastic differential equation. To introduce active transport advection in the whole domain, we simply add the drift term. We replace equation 721 with equation 722. The rest is the same, so it is again relatively straightforward to implement this change in a computer. We can reuse our previous computer code. We just need to add the drift term at the corresponding places. In figure 7.2, we present one realization of the modified stochastic simulation algorithm A17 to C17, where 721 is replaced by 722. To visualize the results of our molecule-based model, we divide domain 0L into 40 bins, and we plot the number of molecules in each bin at time t is equal 15 minutes. This visualization enables a direct comparison with the results of the compartment-based approach, which we have calculated using the Gillespie algorithm and presented as a video today. A snapshot from this video is given in panel A of figure 7.2. Considering the spatial histograms, the results calculated by one realization of the Gillespie algorithm are indistinguishable from the results calculated by the molecular-based model. This brings me to the end of lecture 18, where we have discussed section 7.1 covering stochastic simulation algorithms for diffusion advection processes and section 7.2 covering reaction-diffusion advection stochastic simulation algorithms. Please read pages 193 to 199 of the lecture notes before watching the video of lecture 19. In our next lecture, we will conclude our discussion of chapter 7, where we only cover some selected topics. In our next lecture, we will discuss section 7.3 on bacterial chemotaxis and section 7.4 on collective animal behavior. Thank you very much for listening to lecture 18 of our course on stochastic modeling of biological processes. Bye bye.